Okay, thermodynamics has to do with, and I'm going to humanize the atoms a little bit here, which I tell you guys not to do, but thermodynamics is basically, will the reaction happen? Okay. Basically, we're trying to answer the question of, does the reaction want to happen? Okay, that's kind of the focus of thermodynamics. Thermochemistry is about the energy that you need to put into a reaction or is released from a reaction. But thermodynamics is basically, does it want to happen? Does the reaction want to happen on its own? Okay, or does it not want to happen? A good example of this is, did I show you guys the hydrogen balloon where you blow up the balloon, makes a fireball? Okay, I showed you that, right? This is the reaction for that. I'm not going to balance it, so please don't sue me. Okay, but this is, actually I'll balance it. It's bothering me now. Okay, so this is a reaction, right? Super exothermic, right? That's why there's a fireball that forms. Now, every reaction is technically reversible, and thermodynamics basically helps us understand which direction does it prefer to go in, and is it likely to happen on its own? That's kind of the question we're looking at with thermodynamics, okay? So let's do a little bit of review just so we're familiar with the terms that we're talking about. There's a difference between temperature and heat when it comes to chemistry. Again, you guys don't need to write down unless you have to. We've already talked about this. Temperature is how much energy, how much the molecules move, and that affects the temperature. Heat describes the flow between two substances. So easy way to distinguish this, temperature can be about one object. One object can have its own internal temperature, right? But heat has to do with two objects and how energy moves from one of them to the other. That's the difference between temperature and heat. We talked about the first law of thermodynamics. Energy is neither created nor destroyed. And energy transfers are due to molecular collisions. Basically, when molecules hit each other, that's how the energy is transferred. We talked about endo-exo, basically whether it absorbs or releases energy into the environment. And this is the part that we're going to start that's new, okay? State functions. We've talked about state functions, and we've talked about enthalpy already. Remember H, delta H? Now there's two new ones, and I'm going to recommend that you guys write this down. The first one is entropy, and the second one is free energy, okay, denoted by S and G. Okay, so we talked about enthalpy already, but now we have two new ones. We have entropy, which is S, and now we have free energy, which is G. And these are the three variables that we'll be looking at during this unit. So make sure you guys write that down somewhere. Okay. Enthalpy, entropy, and free energy. HUSG, HSG. So make sure you don't have to write everything down. Just know enthalpy is H, entropy is S, and free energy is G. Okay. So one thing I do want to make sure you guys are aware of is that a lot of times on the AP test, they're not just going to give you delta H, S, G. They're going to have this little like degree sign on the top right. That just means that we're talking about standard state conditions. And then standard state, we've already talked about standard state. It's when all gases are 1 atm, liquids and solids are pure, 1 molarity concentration, et cetera, et cetera. We've talked about this already. So just keep in mind, these things are basically the same thing. It's just that if you have that little circle on the top right, it means it has to be about standard state. And I believe standard state is denoted in your AP equation sheet. So don't stress about memorizing that. But I did want to point that out so you guys don't get confused. They're not different things. One of them is just in general, the one without the degree sign, but the degree sign means that it's in standard state. Okay. Okay, now we're going to get into the actual like content, but any questions about anything so far? Pretty straightforward, just definition stuff, right? Okay, we're going to be talking about enthalpy of formation. So we're going to focus on the three things we talked about: enthalpy, entropy, and free energy. Let's start with enthalpy. Okay, make sure you guys, you probably paraphrase this somewhere, but enthalpy of formation, we also call it heat formation, is a change in energy that takes place when 1 mole of a compound is formed by its component pure elements. Okay, we've actually learned this before, but basically what this is telling us is that delta H is going to be, or delta H of formation is basically when you have pure elements and they combine to form 1 mole of a product, whatever your product is. Okay, that's what the delta H of formation is going to be. It's when you get pure elements and you make 1 mole of a specific product. Okay, and hopefully this rings a bell because we have learned this before, but it has been a long time, so we'll go over how to do this. Delta H of formation is when the energy it takes, or the energy that's released or absorbed when you get pure elements to form 1 mole of a product. Okay. All right, so we are going to look at an example right here. One example, this is the enthalpy formation equation for methanol. So if you guys look at the product, what is the product made out of? It's made out of carbon, it's made out of hydrogen, and it's made out of oxygen, right? Those are the 3 elements that make up methanol. Now, the delta H of formation is the energy that has to do with this reaction when the pure elements make up this product. So this guy is made out of C, H, and O. And the pure forms of these elements is solid carbon, oxygen gas, and hydrogen gas. And so when we have a product and we're looking for the delta H of formation, we're just looking at the reaction where the reactants are the pure compounds. Okay. And so you don't need to memorize these. They'll usually have them out for you, but just keep that in mind. That's the equation that we're talking about. Okay. The one thing I do recommend memorizing are the diatomic gases. So just know that oxygen's pure form is O2, hydrogen's pure form is H2, nitrogen's pure form is N2, chlorine is Cl2, F2. Okay, so those are kind of the common ones. There's some more, but I'd say those are the ones you'll see the most. Okay. And I'm sure you guys are kind of or subconsciously aware of this already. You've probably seen that most of these elements, they kind of show up in this form. This is the most stable form. Okay, so now let's talk about what we can do with this concept. So if the delta H of formation for a compound is negative, right? Obviously, if delta H is negative, it is exothermic. It's releasing energy. So I guess I could write it right here. If the delta H of formation, same thing as regular enthalpy. If it is a negative number, it's going to be exo. And exo means it releases energy. Okay, and then the opposite is true as well. If delta H of formation is positive, it's going to be endo, which means it absorbs energy. Okay. Now let's see if you guys remember. If you touch an exothermic reaction, is it going to feel hot or cold? So who thinks it's going to be hot if you touch something that's exothermic? Who thinks it's going to be cold? Exo. Okay, so this is going to be hot because remember, you are not exo. The reaction is exo. I know that we are very egocentric. I'm probably the most narcissistic person here. But if this is the reaction, right? You have a reaction in a beaker and it is releasing energy. And then this is your very beautiful hand, right? Your hand touches it. It looks like a chicken leg, right? I'm missing a couple. Okay, this is your chicken leg, and then you touch it with your chicken leg. If the reaction is giving energy to you, obviously that's going to be hot, right? That's why if you touch a fire, it's hot. But let's look at the other way. If the reaction is endothermic, it's going to be absorbing energy. So what's it going to do if your chicken leg touches it? It's going to feel cold because it's going to take away energy from you, right? You guys are all very hot in terms of energy. You guys make energy, you release energy. And so this reaction is going to take the energy from you if it's endothermic. Okay. Not calling you guys hot in terms of attraction. I'm talking from a pure chemistry, energetic point of view. All right, so just keep that in mind because this will actually help you guys out on some of the FRQ questions where they have a little bit of the more real world application. Okay, if the reaction is exo, it's going to feel hot to you or warm, right? And if it is endo, it's going to feel a bit cold to you. Okay. All right, so this is going to be our equation for finding delta H of formation. Now this sigma just means the sum. So this right here is the Greek alphabet letter for sum. Basically the sum of all the products minus the sum of all the reactants. If you played Mega Man, you might know what this is. The final boss is called Sigma, and this is his symbol. Maybe you guys are too young for that. But yes, you know. Thank you. Huh? Yes, from the X series. Oh, you're a real fan. Okay, my fault. Yeah, Sigma is from the X series. Yeah. The worst ending to a series. If they ended on a cliffhanger because they ran out of money.
No way.
They did. Yeah, so sigma means sum. Okay, so we're gonna jump right into a problem, and I'm gonna actually have you guys try this on your own. Okay, based on the equation we just had. Okay, so I want you guys right here to find the delta H for the reaction below, and I give you the enthalpy of formation for all the compounds in there. I want you guys to try to use the equation we just learned about, and I want you guys to calculate the delta H of formation for this reaction right here. So try it out. Shouldn't be too bad. Just think about how we can plug it into the equation. All right. Okay, so what we want to do is we just want to plug in the data that we have here into the equation that we have. So if you guys notice, we have the delta H of formation, and it's going to be products minus the reactants. Okay, so we're going to start on the product side first for the left side. Now, if we look on the left side, the first compound that we have is CO2. So we're going to look up the number for CO2. And it tells us that it's going to be negative 394. Okay, but if you look at the units of measurement, it's kilojoules per mole, right? How many moles of CO2 do we have in the equation? 2. So what we're going to have to do is we're going to have to multiply that by 2. Okay, now we need to get all of the products. So the sum means adding. So we need to add that to 4 moles of water, which is negative 242. So this right here is going to represent the enthalpy of formation for the products. Okay, so all we're doing is getting the molecules in the products, multiplying it by their enthalpy of formation, and then afterwards we are going to subtract it. And what we're going to do is we're going to subtract it by the same thing for the reactants. Now we have methanol, 2 moles of that, negative 201. And if you notice, we have 3 moles of oxygen, but oxygen is 0, right? So that's going to be 3 times 0, which is 0. You didn't even need to write this part down. Okay, and this is going to be the delta H of the formation of the reactants. Okay, so I'm not going to bore you with all the calculations. I probably did it wrong, though, as usual. But I got negative 1354 kilojoules for my final answer. Everyone got that? Something similar? All right, so that's going to be the delta H of the reaction. Okay, so that's how you find the delta H, the enthalpy of formation. Now let's look at it for a very specific qualifier in this reaction. Now it's asking you to find the enthalpy of combustion for 1 mole of methanol. Now, methanol is going to be CH3C or CH3OH, and it's asking for the energy for enthalpy for 1 mole of methanol. If you look at the reaction, how many moles of methanol do we have in there? Yeah, we got 2 moles, right? Because we got a 2 as the coefficient. So if you want to find it for 1 mole, super duper easy. We're just going to take the enthalpy of formation that we found. Now, we see that the enthalpy of formation is negative 1354 kilojoules, and that's going to be per 2 moles of methanol, right? So we can just set up a very easy fraction. In the problem, this problem, we're asking for 1 mole of methanol. And so if you solve for X, you should get the enthalpy of combustion for 1 mole of methanol. Okay, so I'll give you guys like 30 seconds to do that. It should be a very simple algebra problem. And then after that, we'll go over the answer, and then we'll try part C, and then we'll be done with that one. Alrighty, guys, so algebra here should have been really easy. You just do 1354 divided by 2, and so that should give you 677. So the enthalpy of combustion is 677 kilojoules. If you want to get super specific with the units, you can say per mole of methanol. But if you just put the kilojoules, that should be totally fine as well. Okay. All right, so let's move on to part C. Now it's asking you how much heat is released when 5 grams of methanol is combusted in excess oxygen. So this is a stoichiometry problem. I know it's been a while since we actually did normal stoichiometry. So I'm going to give you guys about a minute or two to try solving this out. Use the balance equation, and you're also going to need to use the numbers that we just calculated as well. So try that out. It's been a while since we did it, so you might want to refresh your memory. You can talk to the person next to you, but it's just basic stoichiometry. I want you to find how much heat, so kilojoules, that's released when 5 grams of methanol is combusted in excess oxygen. Okay, so take about a minute or two to do that. Easy. Okay, so if you guys look at the problem, our starting value here is going to be 5 grams of methanol, and we want to convert that into the heat that is released in this reaction. Just a little too low, or should I move it up a little? Move it up a little. Okay. 1 sec. Okay, hopefully that's a little better, but I'll do it up here. Okay, so we're going to start with 5 grams of methanol. Okay, now we need to use the balanced equation because that's what this value right here applies to. It applies to the balanced equation. So what we're going to do is we're going to set up a fraction so that we can convert this into moles, right? Because chemical reaction is always talking about moles. So the molar mass of methanol is 32 grams per 1 mole of methanol. 32, right? Because CH4 is 16, oxygen is 16, that's 32. Okay. And then there's 2 moles of methanol in the reaction. And then each mole of methanol is going to be negative 1354 kilojoules. Okay, so there you go. That's the stoic setup that you wanted to do. 2 moles of methanol, right? If the enthalpy of formation is a part of the reaction, right? So 1354 kilojoules is one of the products. And so all we need to do is plug this into the calculator, and that should give us the correct answer. And I got negative 106 kilojoules. So if you combust 5 grams of methanol, it should release negative, or it should release 106 kilojoules, and this is exothermic. Okay. So if you had trouble with that, make sure you brush up on the stoichiometry, because it's kind of a fundamental part of chemistry. I know we haven't done it in a while, but just make sure you're comfortable doing that. All right, any questions with any other parts in that problem that's showing? Okay, so that should be enthalpy. Now we're gonna move on to some of the new concepts that we talked about. Okay. All right, let's talk about entropy. Entropy is S, and the definition of entropy is randomness or disorder in a system. Okay, so easy way to think about it is entropy is randomness. Entropy is randomness. Okay, so easy way to think about randomness, because when I first learned about entropy, I was like, what the heck is he talking about? Like, what do you mean a randomness in a system? Okay, so let's pretend that we have an ice cube. Okay, now an ice cube is made up of individual water molecules, right? And the colder it gets, what happens to the movement of the molecules? Do they move more or they move less? They move less, right? So as the temperature decreases, any molecule, right? Doesn't matter if it's water, doesn't matter if it's a gas that, like oxygen gas, the lower the temperature goes, the less movement there is, right? The less movement there is, the less randomness there is, right? Because if something is not moving a lot, there's not a lot of variation in the movement, right? Like for example, if you have a little kid super high on sugar, that kid's gonna be running around everywhere, right? And the kid, since there's more movement, there's more randomness in what can happen, right? Can run into a door, can run out the door, run into a window, jump off the ceiling, jump off the roof, get hurt, break a table, run into you, right? The more movement there is, the more randomness there is, right? So the less movement there is, the more randomness there is. Okay, and the more randomness there is, by definition, it means, oh wait, sorry, less movement does less randomness. My fault, crazy. I was thinking about the toddler still. Okay, the less movement there is, the less randomness there is. So the entropy of the system is going to go down. Okay, makes sense? All right. Now, the other extreme of that would be if you have like a super crazy hot gas, right? Because if you have a hot gas, the molecules are super far apart from each other. And what are they doing? They're flying around like all crazy, right? And then by definition, that means that there's more randomness. It's like that toddler. So the higher the temperature, the more movement there is. And the more movement there is, there's going to be an increase in randomness. And there's going to be an increase in entropy. So good example is, you just want to think about the two extremes, at least that we talk about in this class, solids and gases. Okay, and a key thing you might want to write down is that entropy is always a positive value, because zero entropy means that there is zero randomness. Zero randomness means that there is no movement. And that means that's honestly physically impossible, because everything is connected in the universe. And so even if I fart here, that in some way is going to affect some super far away molecule, because it's going to affect the gas molecules, and it's going to hit that. It's going to be the temperature that comes from my fart is going to dissipate. And in some little way, it is going to affect that system. Not a lot, but a little bit. Yes, it's like the butterfly effect, right? A butterfly flaps its wings and it can cause a hurricane because of the way it moves the air molecules. So same thing. You can't have zero entropy because there's always motion in the universe. Everything is connected. Now, one key thing I do want to mention, and this is kind of, I guess, not about the test, but I think it's pretty interesting, but the entropy in the universe. Do you guys think the entropy in the universe is increasing or decreasing? Think about the universe. Is everything is the randomness increasing or is the randomness decreasing? Okay, so hold on to that for a second. If you guys have taken Earth science, you guys know about the Big Bang, right? Okay, what does the Big Bang say? Yeah, everything started from the same spot, right? So if everything was in the same spot at one point, was there a lot of randomness there or a little bit of randomness? Little, right? There was less randomness when everything is in one spot. But what happened at the beginning of the universe? Went boom, right? And then everything spread out. And we know this because if we look at the movement of the galaxies, every single galaxy in the universe is moving away from each other. Okay, which kind of implies that they all started closer to one another. And so what that means is as things move out, as they spread out, right? Like just like how a solid, everything is kind of in one place. As things move out, the energy is going to dissipate. And so that means that the entropy of the universe is always increasing. Okay, so just keep that in mind. Entropy has a tendency to increase. Systems want to become more random. Systems want to increase their entropy. Okay, just keep that in mind. And that's the reason why, like, your car breaks down, even though you're not really doing anything to it, right? You're just driving it around. It's everything that you use starts breaking. That's why you start breaking down, because there's going to be more randomness in your system, right? You don't want randomness in the way your heart works or your biochemistry works, right? But every system wants to break down. And so that's the reason, that's one way of thinking about how entropy is always going to want to increase, okay? Unless there's some external force preventing that randomness, okay? Any questions? Entropy? And same formula. If you want to find this change in entropy, it's going to be products minus reactants. And this kind of leads, sorry, this is what I really like to think about, but like, this kind of makes you wonder, how could random chemical reactions produce complex structures then? Because if entropy tends to increase, right, you would expect things to get more and more simple, right, to break down. But we have instances where random reactions make more complex systems, like cells, right? Where did cells come from? Where did more complicated organisms come from? If entropy is the law of the universe, tends to make things break down, why are more complex structures forming? Anyway, something to think about. Okay, let's move on to Gibbs free energy. Okay, Gibbs free energy, or simply free energy, is denoted by G, and G is a G is a measure of whether or not a process will proceed without the input of outside energy. Basically, this is asking, will it happen? Okay, does it want to happen? Does a reaction want to happen? There's more things I want to say about entropy now. There's too many things that happen, there's too many complications with it. Because if entropy, sorry, I'll keep going. If entropy makes everything want to spread out, right? How did the Big Bang happen? Because that means all the matter had to come to one spot, right? But then if the law of the universe is everything spreads out, how could everything come to one spot? It's the beginning of space-time, yes.
So what does that mean? The universe exists at that point somewhere.
So where did the energy and matter come from then? The entropy throws a big wrench into all these like questions, like things. We're like, oh yeah, we know how the universe started, but where did the starting materials come from? It doesn't make sense. Yeah. So entropy is very interesting. It's like it's undeniable, right? We all know things break down. We see it in the galaxies. We see it in our fart, right? When you fart, what does it do? Spreads out, right? Entropy, more randomness. But then it kind of throws a wrench into some of the ways that we look at the universe, like the origins and where did life come from. Yeah. Entropy is interesting. Anyway, Gibbs free energy. We'll talk more about entropy later. Okay, so this is a formula for Gibbs free energy. Same thing for the change of enthalpy or entropy. But I want to make sure that you guys write this down. I want to encourage you guys to write this part down because it'll tell us what information we can gather from our calculation. So if delta G is negative, the reaction is thermodynamically favored. What does that mean? It wants to happen. Okay. A term that they used to use a lot, not so much now, but you might hear it, is the reaction is spontaneous. So it'll want to happen on its own. Okay, and if the delta G is positive, obviously it's going to be the opposite. It tends to not happen. Okay, which, and another term for that is not unspontaneous, non-spontaneous. Okay. And if it's at zero, reactions at equilibrium. Okay, so a good example of this is there's this one compound that's super duper explosive. If you literally just leave it there and you turn on the lights, it has a chance to just blow up. Hold on, let me look up what the name of that compound is. You guys don't know how to make it, so. Oh, azide. You guys can do some more research on this if you want. I had a blast thinking about it, but it's called azide. And basically it's super duper, very highly reactive and explosive. It is very spontaneous. The Nazis wanted to use it in World War II, but they had a problem transporting it because what would happen is it would react with literally anything. Like you breathe in the general direction, it sometimes blew up. Sometimes there were reports where they were just chilling. They put it on like a petri dish and it would just blow up by itself. They would turn on a light when they walk in the room and it'll blow up. And so, you know, it's a pretty dangerous chemical when even the Nazis don't want to use it. And so azide, if you guys want to look more into it. But that's a good example of a spontaneous reaction, right? Because it's just looking for a reason to blow up. Another example of a non-spontaneous reaction would be like a rock reacting with air, right? It happens, but like very, very, very slowly, right? It just kind of sits there and doesn't do anything. So those would be like the two extremes of that. And then we have everything in between. All right, any questions? Okay, so what we're gonna do now is we're gonna start combining all this together. Do you guys want to take your break now or a little bit later? Later? Okay, oh, my fault. Okay, so let's go into it. So now we're gonna combine all three of the things we just talked about. Enthalpy, entropy, and free energy, and this is the reaction that we get. Okay, so make sure you write down the reaction, and then after that, I'm gonna kind of explain a couple things. Okay, so free energy is equal to enthalpy minus temperature times entropy. And temperature, we're obviously talking about absolute temperature. Chem, we're always talking about absolute temperature. All right, so let's talk about what this equation is about. So nature, we talked about this earlier, right? We said that the universe, right, like everything in the universe is slowly spreading further and further apart, right? And if things spread out further and further, does it get hotter or colder? If you're right next to somebody, is it warmer or colder? Warmer. And then if you move away from that person, you get colder, right? So as things spread out, they get colder, right? Because heat is a measurement of what happens when things collide with one another, right? So if you're super far away from each other, the chances of you colliding is a lot less, right? So the universe, as everything spreads out, it's going to increase in entropy. So it's going to increase in entropy, but it's going to decrease in energy. That's what the universe wants to do. Okay, so the law of entropy shows that basically the universe wants to decrease in energy and to increase in entropy. Things want to break down and things want to get colder. And this is where we get this equation from. Now, one thing I do want to mention about this equation is that a lot of times entropy is going to be given, or enthalpy is going to be given to you in kilojoules, but a lot of times they're going to give you the number for entropy in joules. Okay, so just make sure you guys keep an eye. That's what these bullet points are. Just keep an eye out for that. Make sure you're consistent in your units of measurement. Make sure that if they give you entropy in joules, that you convert it to kilojoules. Or if you want to convert this into joules, you can do that as well. But just make sure that everything is in the same units of measurement. Typically, I recommend doing kilojoules for your for the AP test, because that's what they like for delta G. So I recommend converting everything to kilojoules. But if you're more comfortable with the bigger numbers, the zeros at the end, that's totally fine, as long as you keep the units of measurement consistent. Okay. All right, now we're going to start using this equation to solve some practice problems. Okay, you guys ready to go? But before we do, I wanted to go over this graph. You don't need to copy this down. You can kind of memorize it. Remember what we said about earlier, that if delta G is negative, the reaction is favored, and if it's positive, it's not favored. Well, I want to help you guys out, so I got this chart for you that I did not make. I don't want copyright infringement, but this is a chart that you can use to kind of think about whether or not a reaction wants to happen or not. So if H is really big, so let's look back at the equation. Delta G is equal to delta H minus T times delta entropy. If H is a really big number, like it's like 1,000, okay, and then this, or it's a positive number, sorry, it's positive 1,000, and if the entropy is a negative number, right? It's minus. We know that temperature is always positive, right? Because you can't have a negative absolute temperature, so this is a positive number. If entropy is a negative number, this is going to be a positive, right? Because double negative, it'll become positive. So that means your delta G will always be positive. Make sense? And it's going to be non-spontaneous. So this chart is basically getting some information out of the equation. Again, you don't have to memorize this. I'll be honest, I have not memorized this. But this is a good way to kind of check your answer while you're doing your homework and studying, to see if you are getting the right answer for whether something is spontaneous or not. Okay, things get a little bit trickier with temperature because it's going to affect the size of this value right here. So just make sure you're plugging in your values. But there will be questions on the AP, or there might be questions on the AP test where they don't give you any numbers. They just say high temp, low temp, and you'll kind of have to use this equation right here to figure it out. Okay, so just make sure you guys are comfortable deriving this information. If anything, you should be able to figure all this stuff out right here, the spontaneity, based on whether or not these are positive, negative, or high or low. Okay, just keep that in mind. And then I thought we had a practice problem, but we have one last thing. Talk about voltage and favorability. This is kind of a niche part of the exam. You might have like 1 or 2 questions every couple of years about this, but I do need to talk about this. But we're going to be talking about redox reactions next time we meet. And we talked about it last, I think in unit 4, but redox reactions, they're favored if the potential has a positive value. And this is the equation that we use, okay? Delta G is free energy, N is the number of moles of electrons, F is a constant, you have this on your equation sheet, and E is the standard potential, okay? And you should usually be provided with this as well. And then same thing, if E is positive, G is negative, and then the reaction is favored. If E is negative, then G will be positive, and it'll be thermodynamically unfavored. Okay, so just another application of what we just talked about. I just need to go over it just so that you guys are aware. But we'll talk more about redox in the next unit, which is Monday. So today's a one-day unit. And we're just going to be finishing off with a bunch of practice problems. All right, you guys ready to try one? Okay, let's do 13.2. 13.2 is going to use the information up here. So just keep that in mind. I'm going to help you guys out because we haven't done redox in a really long time. So if you remember what redox is and how to find the difference between them, please feel free to try this out. But I know it's been like months since we even talked about use that term. So I'll go over step by step. So the acronym that you want to use for redox is oil rig. Oxidation is loss. And then rig reduction is gain. So whatever loses electrons is being oxidized. Whatever gains electrons is being reduced. Okay, so basically what we want to do is we want to line up the elements that we have here. And we want to figure out as we go from the reactants to the products, is it being oxidized or is it being reduced? Is it gaining electrons or is it losing electrons? Okay, now this part I think you guys can figure out on your own. So I'll give you guys about 30 seconds. I want you guys to figure out which element is being oxidized and which one is being reduced. Okay, so 30 seconds to do that. All righty, guys, time's up. Let's go over this. So if you take a look at zinc, right? Zinc has a charge. What's the charge on solid zinc on the left side? Yeah, it's neutral. It's 0. Okay, but if you look on the right side, what's the charge? +2. So if you go from 0 to +2, are you gaining or losing electrons? You are losing. Oh, I'm so happy you guys remember that or can figure that out. So you're losing electrons because you're going from 0 to positive. You're losing something that's negative, which is going positive charge. So your zinc is losing. So zinc is being oxidized. I guess I'll just write oxidized right here. And then that means that silver needs to be reduced. Okay, so zinc is oxidized, silver is reduced. If you guys didn't get that, make sure you go over oxidation reduction real quick because on Monday, we're going to go into a new unit and that's going to be all about oxidation and reduction. And you're going to have to be able to do it like really, really quickly. So if you take a look at this, what this tells us is that electrons moved from zinc to silver, right? Because if zinc is losing electron, it needs to go to the other element. Now, let me ask you guys, how many electrons were transferred? Show me with your fingers. How many electrons transferred from zinc to silver total? I see like blank faces and a bunch of peace signs. Yeah, it's going to be 2. It's 2 electrons because if you guys look at this, it's going to be 1 element of zinc. And then if you notice, there's 2 silvers, right? Zinc becomes +2. That means it needs to lose 2 electrons. Okay, now since there are 2, and if you take a look at this, silver went from positive to 0. That means silver received the 2 electrons that zinc gave up. So the number of moles is going to be 2 electrons. 2 moles of electrons moved. And that's going to be important because we're going to need moles of electrons for our equation. All right, from there, very simple. You just need to plug and chug. Okay, you're looking for the delta G value. So let's plug in what we got. We got negative. Okay, what number should we put in for N? Yeah, 2. -2. What's the number for F? Yeah, 96 500. And the units of measurement is going to be coulombs per mole. Oh, and then this is going to be moles. And then our energy is right here. It's positive 1.56 volts. And I'll do the math for you guys. You're going to get negative 301,000 joules per mole. Okay. And the reason why these are the units of measurement, because coulombs can be broken down into smaller units. I'm not going to, and volts can also as well. I'm not going to go over how the units break down. That's more for physics, but this is going to be your answer. The numbers should be really easy to get. You just multiply the three of them together. Okay. Alrighty, guys. So we'll take our 5-minute break. If you need to go to the restroom, go to the restroom. The next problem is pretty long. It's a multi-part question, so I want to give you guys some time to rest your brains a little, and then after that, we'll go over that problem. Okay, so take a 5-minute break. Alrighty, guys. So if you guys are finishing up, please feel free to finish up. But I'm going to start going over this problem. So what we want to do is we want to combine reactions 2, 3, and 4 so that we can create reaction number 1. So what you first want to do is you want to make sure that you put everything in the correct spot. So if you notice, reaction 1 has N2H4 liquid on the left side. So if you look at reaction 2, you got N2H4 liquid on the left side. So we're just going to copy that down. N2H4 plus CH4O, and then that's going to form CH2O plus N2 plus 2H2, and that's going to have an enthalpy change of negative 37. Okay. Next, if you're going to move on to reaction 2, now you want to have NH3 on the right side, and so if you notice, reaction 3 has NH3 on the right side. And so what we're going to do is we're going to make it so that we have NH3 on the right side. So I'm going to put 2NH3 and 2 plus 3H2, and there we go. And then our delta H for that reaction is negative 46. Okay. So far, so good. Now, if you guys really want to, you can start canceling some things out already. Like you can see that N2, you have it on the reactant side and the product side. So these guys are going to cancel out. You got 2H2 here and 3 of them here. So this will cancel out with the coefficients, leaving just 1H2. All right, so if you guys notice, we pretty much have what we want, right? We want N2H4, H2, and 2NH3, but we have this pesky CH4 on the left side that we want to get rid of. And so if you notice, reaction 4 has CH4O on the left side, but we can't put it on the left side. We want it on the opposite side so that it can cancel out. And so we're going to flip this reaction right here so that we have CH4O on the right side, and then CH2O and H2 are going to go on the left side. Okay, so if we do that, and hold up, if we switch the reaction, we're going to have negative 6 or positive 65 for the enthalpy change. Okay, so we can start canceling some things out. We're going to cancel out the CH2Os. We're going to cancel out the CH4O, and I messed up somewhere. I messed up. Oh, I think I wrote it wrong. Sorry, guys. This should have been a 2 right here. My fault. Sorry, guys. Yeah, that's impossible. Yeah, it should have been a 2, and that's where we get the 2. My fault. My fault. I wrote it. I copied it down wrong here. So if you guys got that, and that was what was tripping you out, I'm really sorry about that. But as you know, I make a lot of mistakes. And so if you combine these reactions, you'll get this, which is what I wrote earlier for reaction 1, right? And so this is your final reaction. And so all you need to do is combine these reactions together. Now, the only thing you really had to do was flip reaction 4 so that it's positive 65. And so if you combine them all together, you should get an enthalpy change of negative 18 kilojoules per mole of reaction. Sorry about that, guys. I was plagiarizing a problem and forgot to copy down one of the coefficients. That makes sense because it wouldn't be okay, whatever. All right, we're good to go on that one. Okay, so just a quick example of Hess's law. Make sure you guys are comfortable with that because we'll be using that for a variety of parts on the AP test. Okay, numbers 13.4 and 13.5 are going to be multiple choice questions. And so I'll give you guys like 3 minutes to try both of those out. I have the reactions that you're looking for on here, so you can refer back to that, but try to solve 13.4, 13.5, use your notes if you need to. But yeah, I'll give you guys about 3 minutes and then we'll come back together. Okay, let's start with 13.4. So it's saying that if the reaction were repeated at higher temperature, how would the reaction value for delta G be affected? Now, if you guys remember earlier, we have the delta G equation is delta H minus T times delta S. And it's telling us that we are increasing the temperature right here. We are increasing the temperature. So we can already think about, you could look back at that table to kind of look at it, but you can also just derive some information right here. If you are increasing the temperature, that means that this entire value right here is going to get bigger, right? So if this value is getting bigger, is the value for delta G going to get bigger or smaller? It's going to get smaller because we have H, delta H, right? Delta H is not changing. And if you're subtracting from it, the number that you're subtracting is getting bigger. You're subtracting less and less, which means eventually this will become smaller and smaller. So we don't know if it's going to be a negative number or not, but we know that it's going to be smaller and smaller, which means that we can cancel out B and we can cancel out D right away, because becoming more negative is just another way of saying it's going to get smaller. And so it's not going to get more positive and it's not going to stay the same because you are changing a variable. So B and D are obvious ones that are going to go out. Okay, so from here, it becomes pretty simple. We got A and we got C. Now, these two things are the same, but the reasonings behind it are going to be what we're looking at. A is talking about entropy, okay, whereas C is talking about higher pressure. Okay, now, entropy is kind of hard to think about just by, actually, we can look at entropy right here. So if you look at this, both of these are liquids, right? Okay, and if you look on the right side, what state of matter are all these guys? Gases. So let's think about it. Which one has more entropy, liquids or gases? Yeah, gases have more entropy. Okay, and so it's saying it's going to get more negative because entropy is getting bigger. Okay, so that's a possibility. A can definitely work because it matches up with our math. If S is getting bigger, if S gets bigger with the temperature, it's going to have the same result on the Gibbs free energy. Okay, but if you look here, it says it's negative because the gases will be at higher pressure. If you look at this equation, does this have anything to do with pressure? No, right? We don't even have anywhere to put ATM or PSI or torr in there. So C would not work. A would be the best answer because entropy will be the driving force behind it because you're going from liquid to gas and there's nowhere to even put in pressure into this equation. Okay, so A is the best answer. Make sense? So again, all we're doing is deriving things from this equation right here. Oh my God, we're almost done. All right, let's zoom through 13.5. So under which of these conditions would reaction 3 be thermodynamically favored? I'll just let you guys know it's going to be C. Okay, C is correct. And so because if you look at this, if we look back at the equation, okay, if we take a look at the left side and the right side of the equation, how many moles of gases are on the left side? 4. We have 4 moles. And then if we look here, how many moles of gases do we have here? There's 2. So if we go from 4 moles to 2 moles, is there more or less entropy? Yeah, there's less entropy. So entropy here is going to be negative because it's becoming less complex. It's getting less random, right? What's more random? 4 crazy kids running around or 2 crazy kids running around? 2, right? That's a little less random. So entropy will always be positive for the universe, but systems can have negative entropy. Yeah, so the net in the universe will always increase, but I mean, like if you take random metals and you build a car, obviously you're taking more randomness and building something a bit more complex, right? So yeah, sorry if I misspoke about that, but you can have negative entropy because or you can have negative change in entropy. Sorry, I think I said regular entropy will always be greater than 0. I'm sorry, that's my phone. Okay, entropy will always be greater than 0, but delta S can be negative, right? Because you can go from less complex or more complex to less complex. Okay, and so delta S will always be negative, and so we look right here, and if enthalpy is also negative, we got a negative here. Temperature is always positive, right? And so that means that the only way for us to get something that is thermodynamically favored, for this to also become negative, is if temperature is very small, right? Because temperature has to be very small in order to not cancel out the entropy. Okay. So kind of complicated, but again, everything kind of comes from this equation. All right, and we'll end it right there for unit 13. Congratulations, guys. That's a one-day unit. Thermodynamics, just make sure you guys are keeping up with the reading and the homework. The homework will be due next Friday, same day as the exam for unit 13 and 14, and we'll spend the next 2 days on 13 and 14. Yeah, what up?